Hi, everybody. Welcome to our seminar. And today, Eric Culver is going to tell us about distinct eigenvalues from some new graph products. Thank you.
Okay. So yes, I'm Eric Culver. So yeah, this is my talk. So to start off with, as I'm sure most of you know, graphs consist of vertices connected together with edges. This is an example of a graph that will show up quite often in this talk, which is the complete graph on n edges or n vertices. This is has 5 vertices. We denote this with kn, k sub n, and where n is the number of vertices. So this is k sub 5, also known as a complete graph. I already mentioned that. But and the main thing that we're studying here is the inverse eigenvalue problem, where we look at the what's known as the adjacency matrix of the graph, where we have a matrix with the vertices. Essentially, the vertices are giving the rows and columns, and we put zeros wherever there's not an edge between the two vertices. So there's a 0 here because there's not an edge between this 0 vertex and this 2 vertex. And then we want to look at all the matrices that match up with this pattern, essentially. So where the stars are, we can put any non-zero entry, and where these daggers are, we can put any entry. The diagonal entries are special, but where the zeros are, we want to have zeros. And we want to look, essentially, we want to only look at symmetric matrices in this particular case. So we want symmetric matrices, but we can put any entry we want where the stars are and any entry where the daggers are. And in particular, what I'm looking at is how many eigenvalues do we get out of this. So here is an example matrix, which is just the adjacency matrix, where we have all zeros on the diagonal and ones where there's an edge, zeros where there's not an edge. And in this case, the number of eigenvalues that we get is 4. Here are the actual eigenvalues, but we get 4 different eigenvalues. And so that's a lot. What we're trying to do is get not very many distinct eigenvalues. So here is a different matrix that follows the same pattern. So it's still a symmetric matrix. It still has those zeros in the corners. And again, the diagonal can be whatever. But this matrix has only 2 distinct eigenvalues. And this, it turns out, is the smallest amount that you can do with this particular pattern. And for a particular graph G, the smallest number of distinct eigenvalues for a matrix with that pattern is called Q of G. And so this is the value that I was looking at, is this Q of G. Since the matrix needs to be symmetric, the only matrices which will have only one unique eigenvalue are going to be multiples of the identity. And so the ones that have Q of G equals 1 are those matrices that have no edges whatsoever, not very interesting whatsoever. And so Q of G equals 2 is the next interesting case, and it turns out it's incredibly interesting trying to figure out which graphs have Q of G equals 2. It's hard to figure it out. So here are some graphs which have Q of G equals 2, all complete graphs. There's a family of graphs which are called double-ended candles. At least the paper that found them called them that, which are these like you kind of take two paths and connect them together with these X's and then close them off with these triangle looking things. And then so that family of graphs has Q of G equals 2. Also this sort of like barn or house looking graph, which actually, I forget the exact result. There's some result where like all graphs of a particular type contain this as a subgraph or a subdivision or something like that. I forget what the result was. There's a reason why I included that small 5-vertex graph. But yeah, all graphs of a particular type with Q of G equals 2 contain that. Anyways, but yeah, so here are some examples. Also, something that you should know for this talk is what one factorable is. It's just if you have a graph which is k regular, meaning every single vertex has k edges coming out of it, and also that it is k edge colorable. So you can color the edges with k colors. So essentially you can partition the graph into k perfect matchings. Then this is what one factorable means. This is important for the result that we're going to cover. But so the title of the talk talks about a new graph product. The new graph product is what I call the modified strong product. Maybe not the best of names, but it is what it is. So the modified strong product is like so. So you take two graphs and you essentially add in all of the edges that you would for the strong product, except for the edges that would go across here. So like it's not a commutative product because in the strong product, if you are imagining you did K2 strong product P3 here, you would have some copies of P3 going directly across between these three vertices on the bottom and on the top. And those are missing in this case. And so in the modified strong product, we just have copies of the first graph going down, and then we have these like cross edges. And that's what the symbol's supposed to suggest there. And so yeah, that's what's going on. The definition is attempting to spell that out, but yeah, that's yeah. So the theorem that I want to go over and sort of prove for you today, because I've heard said many times that every talk should have at least one proof, is that if a graph is one factorable, then if it's k regular with chromatic index k, then taking the modified strong product of that graph with k sub k, the complete graph on k vertices, will yield a graph with q number 2. And so this is a way to essentially take those graphs which have a one factor and turn them into a graph which have this property that they have a small number of eigenvalues in their inverse eigenvalue problem. So the proof strategy is, since it's one factorable, we can decompose it into these perfect matchings, and then using those, each of those will be, we can turn them into block matrices essentially, and those block matrices, since they're a bunch of like K2s, their eigenvalues will just be -1 and 1. And so then we can then use those block matrices to construct a bigger block matrix for this modified strong product. And it, by using the construction that I will explain, it will inherit those exact same eigenvalues of -1 and 1. So that's the basic overview. So since it's one factorable, there's a K coloring of the edges such that every vertex is adjacent to an edge of every color. So let A sub I be the adjacency matrix for the edges of color I. So this is we're essentially writing the adjacency matrix for G as a sum of these adjacency matrices for each color, is the way that I think of it, at least. And so you get one adjacency matrix for each color. And each of these adjacency matrices are just going to be a disjoint union of edges. And so they're just going to consist of blocks that look like this. Maybe the blocks are, sort of spread out over the graph, but they're just going to be 0, 1, 1, 0 blocks. And so they're going to have the eigenvalues -1 and 1, each one of them with multiplicity n/2, because that's how many edges each one's going to have. And so that is the total number of that's the multiplicity of the eigenvalues that each one's going to have. So here's an example of a really small graph, just C4 here. And so we have 2 red edges, 2 blue edges. Here's the adjacency matrix for the full graph of C4. And it is the sum of these 2 matrices, 1 for the red edges and 1 for the blue edges. You can see that if you add these 2 up, you get these. And then each of these is just a block matrix where each block is just a 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, like that. And so there's a lemma that I'm not going to prove, but is proved in the paper, which is on the archive, and will hopefully be published soon. Which is that there are these projection matrices, these J sub i's, with these properties that they annihilate each other when you multiply 2 of them that are of different indices, you get the 0 matrix, and when you square any one of them, you get themselves. But also the more important fact is that they are all non-zero. They have all non-zero entries, so that they have the right pattern. And so an example is for when k is equal to 2, because they're k by k matrices. When k is equal to 2, we have these 2 matrices. 1 half, 1 half, 1 half, 1 half, and then 1 half, -1 half, -1 half, 1 half. So you can do the multiplication yourself. If you multiply these 2 together, they annihilate each other. The square of this one is itself, things like that. And so what we want to do is we want to construct this block diagonal matrix from our A sub I matrices and these J sub I matrices. And so I'm using the Kronecker product to show how I'm constructing this block diagonal matrix. But essentially, it is just where I have a 1 in one of the A matrices, I'm going to put in a J matrix, is essentially what the Kronecker product is doing, is like I'm replacing ones in an A matrix with a block of the J matrix. And so in our example, like remember the A1 matrix had ones up here and ones down here, while the A2 matrix had ones along this the sort of negative diagonal. And so that's what's going on here. I have my J1 going here and here, while the J2 is on the negative diagonal, but in these 2x2 blocks. And so this is our example M matrix. And then what I'm going to show, I believe on the very next slide, yeah, the next slide, is that this M constructed in this way is the exact matrix that has the -1 and 1 as eigenvalues. It inherits the same eigenvalues that the A1 and A2 and up to AN has. But from this example, you can see that it has the appropriate pattern. We've taken G and we've scaled it up by by 2 in this case, because that was the number of colors that we had, because that's the size of our blocks. And the reason why we needed to not use the strong product is because we end up with blocks of zeros along the diagonal. And so that's why we needed the modified strong product. Yeah, this matrix has the pattern of G modified strong product K2. So how do we show that this has the right eigenvalues? Well, we can show that the J sub I matrices share a common set of eigenvalues Q sub J. Partially that's from how they're constructed. If I equals J, the eigenvalue is 1. If I is not equal to J, the eigenvalue is 0. Again, they're projection matrices. So that's essentially from how they are projection matrices. If you have some V1 comma J be an eigenvector for A sub I, the corresponding eigenvalue is either 1 or -1. Then all the eigenvectors for these A sub I Kronecker product J sub K will be of the form you take the eigenvector and you Kronecker product for A and you Kronecker product it with the eigenvectors for the J's, and it'll either have the same eigenvector as it did for the A, or it'll be 0 if it's one of the ones that has eigenvalue 0 for the J. And so when you add up all of those A sub I Kronecker product J sub K's to get M, you get all of the eigenvalues being either 1 or -1, because they're either the same as the A sub I's or they're zeros, but the zeros occur exactly where we have the non-equality index. And so the zeros are where the zeros occur in the places where we have non-zeros with the other J's. And so we just end up with 1s or -1s. And so M has only 2 distinct eigenvalues, the 1 and the -1. And so that is how we prove that. Some other results from the paper, we were able to show that for any connected graph with max degree k, we can do a strong product with a complete graph on k plus 1 vertices and get a q number of 2 for that. And this one is a very similar result. We just have to use, we have to do some manipulation on the diagonal for this one. So we need to add ones to the diagonal to represent the colors that are not being hit on those vertices. So that's why we end up using the strong product, is because we do end up with non-zeros on the diagonal for that one, non-zero blocks. Another result is for larger cliques. So for all of the results previously, we were decomposing graphs into K2s, cliques of size 2, essentially. But for instance, for this graph, which is a Cartesian product of a K3 with a K3, we can decompose it into essentially a perfect matching of K3s, of two K3s. So here's the coloring. We have like in the red columns here, we have K3s going one way, and then in the blue rows, we have K3s going the other way. And so, and every vertex is touching exactly 2, one going one way in the rows and one going the other way in the columns. And so utilizing essentially the same idea as in the proof before, but instead of separating the adjacency matrix into blocks where or into a sum where the blocks are edges, we separate the adjacency matrix into a sum where the blocks are K3s. We can use this to show that this graph, or really any graph that is a Cartesian product of 2 of the same clique, modified strong product K2 will have a Q number of 2. And then generalizing it in the same way that we did before, we can do similar sorts of strong product results where we modify things on the diagonal. All this stuff in the beginning with the conditions here with the hypergraph stuff is just trying to formalize the idea of like we're breaking it apart into cliques, but like how do you explain how you're partitioning it into cliques of the same size, sort of thing. And that's how we came up with explaining it. Well, and then we need to color the cliques. And so, yeah, that's how we explained how to partition it into cliques and then color the cliques. But anyways, so yeah, there's a number of different results along those lines. But so future work that we are attempting to do is how do we partition a graph into complete graphs of different sizes, because all complete graphs have q equal to 2, but so far they have different eigenvalues, and so it's a matter of trying to like change the matrices so the eigenvalues match. And how do you try and like massage that in and make it work? Or maybe is there a way to extend these results so that You could partition a graph into, different graphs with q equal to, or the same graph of q equal to 2 sort of thing. Anyways, those are the things that we're working on. So thank you.
Thank you very much.